lecture is about R's complement, where R is the base or radix of the number system. Complement is nothing but if 3 is a number, its complement in the case of decimal number system is -3. That is 3 plus -3 is equal to 0. So we will learn how we can find out the complement of a number. So before going into the details of how we can find out the complement of a number, what is the requirement of finding or using these complements? We can explore it now. In digital electronics, two types of complements are defined, R's complement and R minus 1's complement. In this lecture, we are focusing on R's complement. Then consider we need to perform 8 minus 3, where 8 and 3 are the numbers in the decimal number system. So this is only a subtraction operation. We know that digital electronics or in digital machines, we are performing this operation, addition, subtraction, division or multiplication with the help of some circuits. And suppose there is a circuit predefined or already there to find the sum of two numbers. It will be good if we can use that circuit itself for finding the difference also by making some modifications. That is 8 minus 3, return back to our example itself, 8 minus 3 can be expressed as 8 plus minus 3. They will produce the same result. That is, we are expressing the subtraction operation in terms of addition operation. 8 minus 3 can be represented as 8 plus minus 3, where minus 3 is the complement of 3. So instead of performing the subtraction operation, we are adding the complement of the number to the first number to get the desired result. In such a way, we can make use of the circuit designed for addition operation to perform the difference operation or subtraction operation. So we can say that complements are used in digital computers to simplify the subtraction operation. How we can simplify the subtraction operation? We can express subtraction in terms of addition. That is, by adding complement of the number to the first number, we will get the same result. This example is based on decimal number system. Then, as we have already said, there are two types of complement, R's complement and R minus complement, where R is the base of number system. So can you say what are the complements available or defined in the case of decimal number system? R's complement, that is 10's complement, and R minus 1 complement, that is 9's complement. So in decimal number system, there are two complements defined, 10's complement and 9's complement. What about the binary number system, where R is equal to 2? So there is 2's complement and 2 minus 1, that is 1's complement. So once again, in decimal number system, 10's complement and 9's complement. In binary number system, 2's complement and 1's complement. Similarly, in the case of octal and hexadecimal or any based number system, we can define R's complement and R minus 1's complement. But mainly, we are focusing or utilizing this 10's complement and 2's complement, and also the 9's complement and 1's complement. This lecture is about how we can find out R's complement in the case of decimal and binary number system. The equation specifying in this lecture can be utilized for any number system, that is with any value of R. So we can see R's complement definition is like that. This equation can be utilized for any based number system, that is R equal to 10, R is equal to 2, or R equal to 8, R equal to 16. Any number system, we can make use of the same formula to find out the R's complement. There are some easy methods to find out 1's complement, 10's complement, etc. that I will explain at the end of the session. But for the time being, we can start studying from the basic equation. So we are going to discuss about the R's complement of a number. Let n is a positive number in base R. Complements are defined for positive numbers. Then let n be a positive number in base R, where R is the radix or base of the number system. Then n is the small letter n is the number of integer parts in n. So if suppose the number is 15.5 in the case of decimal number system. So n is equal to 15.5 and n is equal to, small letter n is equal to, what is the total number of integer part? 15. So 2. Small letter n is equal to 2. Therefore, then r's complement can be expressed as the equation r raised to n minus n for n not equal to 0 and 0 for n equal to 0. We will see more worked out examples based on this equation and it will clear to you. The equation is that r raised to n minus n, where n is the original number given and small letter n is the number of digits in the integer part and r is the base of the number system. If we are discussing on decimal numbers, r's complement, that 10's complement can be found out by substituting r equal to 10. In the case of binary number system, r is equal to 2 and so on. Okay, let's see, or let's study with an example. So as we have already told, 10's complement in decimal number system and 2's complement in binary number system are examples for r's complement. So first question, find the 10's complement of the number 52520. This is a number in decimal number system since the base is 10. So 52,520, right? This number 52520 to the base 10. Then we have to find out the parameters first. What are the how many integers are present? That is number of digit in the integer part. 1, 2, 3, 4, 5. So number of integers or small letter n is equal to 5. Then what is the value of the number or capital N is equal to the given number itself, 52520. Then what is the base of decimal number system? It is given in the question itself. It is 10. So r is equal to 10. So we can simply substitute in the equation 10's complement of 52520 to the base 10 equal to, what is r raised to n, r raised to, that is equation is r raised to n minus capital N. So r is 10. 10 raised to n. N in the value of n is 5. So 10 raised to 5 minus 52520. Okay. 10 raised to 5 is simple. You can directly calculate in your mind or make an use of the calculator. Upon evaluation, we will get the result as 47480. Simple subtraction only in the case of decimal number system. So in order to make error-free calculation, in the exam also you can use calculators. 10 raised to 5 minus 52520. The answer is 47480 to the base 10. So the 10's complement of 52520 is equal to 47480 to the base 10. So the equation is r raised to n minus n. Next, we can see another example. Find the 10's complement of 0.3267 to the base 10. So what is the value of n? The original number, that is 0.3267. Then what is the value of small letter n? Number of integers or number of digits in the integer part? 0, right? All the digits are appearing in the fractional part. So the value of n is equal to 0. You have to understand it carefully. Small letter n denotes the number of digits in the integer part. So 0. Then base is same. So it is given in the question. R is equal to 10. So 10's complement of 0.3267 to the base 10 is equal to, the result is 0.6733 to the base 10. Next, we will see some examples for the computation of 2's complement. Find 2's complement of 101100 to the base 2. Then we can use the same equation, that is r raised to n minus capital N. Here n, that is the original number, n is equal to 101100 to the base 2. Then number of integers. So 1, 2, 3, 4, 5, 6. There are total 6 integers. So small letter n is equal to 6. What is the base or radix of number system? Since it is binary, r is equal to 2. Therefore, 2's complement of 101100 to the base 2 is equal to 2 raised to r minus n. That is 2 raised to 6. Sorry, 2 raised to n, 2 raised to n minus n. So, or r raised to n minus n. Here, the value of n is equal to 6. Therefore, 2 raised to 6 minus The value of n is 1, 0, 1, 1, 0, 0. So 2 raised to 6. How we can compute 2 raised to 6? So there is a shortcut method. We can easily find out. First write the positions of, powers of 2 up to 2 raised to 6. 2 raised to 0, 2 raised to 1, 2 square, 2 cube, 2 raised to 4 up to 2 raised to 6. Then put a 1 over the position corresponding to 2 raised to 6, and all other positions we have to write 0. Then we will get the 2 raised to 6, the binary equivalent of the number 2 raised to 6. That is 1 followed by 6 zeros minus 1, 0, 1, 1, 0, 0, our original number. This is a binary subtraction. I have done it here for your reference. When we perform the binary subtraction, we will get the result as 0, 1, 0, 1, 0, 0 to the base 2. Please don't do this subtraction in the way of decimal numbers. This is not decimal number. Clearly, its base is 2. So we have to perform binary subtraction. I will explain. 0 minus 0, 0. 0 minus 0, 0. 0 minus 1. It's not possible. Reason is that 0 is less than 1. So we cannot subtract. So we have to take or borrow from higher order bit. Then if you check here, here is 0 only. Here also 0. Here also 0. Only here the 1. So we have to forward this 1 to lower significant bits or lower order bits. So 1 is copied to here. So here it will become 1, 0 or 2. From that 2, we are taking 1 to this position. So here it will become 1 only. From 1, 0, that is 2, we are taking 1 to the next lower bit position. So here it will become 1, 0, that is 2. So from here, we have to forward a 1 to next higher bit position. So 1, 0 minus 1, 1 only here. Here 1. And ultimately, we will reach at here. Here the value is 1, 0 or 2. So 2 minus 1, the answer is 1. Here 1, 1 minus 1, 0. 1 minus 0, 0. 1 minus 1, 0. Here is already 0 since we have forwarded this 1 to lower order bit as borrow. So 0. So the answer is 1, 0 or 0, 1, 0, 1, 0, 0 to the base 2. Next, we will see another example. Find 2's complement of 0.0110 to the base 2. So, first of all, what is n? The original number. It is 0.0110. What is the number of digits in the integer part? Look here. All are 0. So, the number of, there is no integer digits. So, or no digits in the integer part. So, it can be written as 0. What is the value of r? 2. So, 2 raised to n. 2 raised to, that is equation is, we know that 2 raised to n minus capital N, or r raised to n minus capital N. R is 2. So 2 raised to 0, 2 raised to n, 2 raised to n minus capital N, 2 raised to 0 minus 0.0110. So 1, 2 raised to 0 is nothing but 1 minus 0.0110 to the base 2. So we have to perform which subtraction? Binary subtraction. It is given here. You can refer. Then the answer will be 0.1010 to the base 2. So the 2's complement of 0.0110 is equal to 0.1010 to the base 2. I will explain the subtraction. 1.0000. We can return it like that. Then we have to copy the second number, that is 0.0110. The alignment must be done like this only. Then only we will get the correct answer. So 0 minus 0, 0. We cannot subtract 1 from 0. So we have to repeat the procedure. So 1 is forwarded to here. So it becomes 102 here. But next again we have to forward a 1 to next higher bit position. So here 1 and here it will become 2. From that 2 or 1, 0 we are taking a 1 to this position. Our ultimate aim is to make this bit position 1, 0 or 2. So here it again 1. So here 2. 2 minus 1, 1. 1 minus 1, 0. 1 minus 0, 1. Here 0 since we have already forwarded. So 0, 0, answer is 0. So if you write these final numbers on the top of the regular digit, then the subtraction process will be more easy for you. So the 2's complement of 0.0110 to the base 2 is equal to 0.1010 to the base 2. Then, so we have seen that the equation used to find out the two's complement of a number in a number system with base r is r raised to n minus n. First, we have to find out r raised to n. Then, we need to subtract n from r raised to n. So it will take some time. So in competitive examination and all, if there is a time is a critical constraint, we can make use of there is a shortcut method to find out this r's complement. Problem with this shortcut method is that shortcut method is different for different number system, but the rule r raised to n minus n can be applied to any number system with a different basis. That is, even though the value of r changes, we can simply change the equation. That is, r raised to, we need to replace the value of r. If you are using binary number system, r is 2. If you are using decimal number system, r is 10, and so on. So next, we will see about the shortcut method to find the r's complement in or tens complement in the case of decimal number system and two's complement in the case of binary number system. Then, how we can find out the tens complement in easy way? First rule says that leaving all least significant zeros unchanged. That we are traveling from the rightmost bit. Okay, and all the zeros in the least significant digit positions are retained as it is 0. That is a 0 itself. Then first non-zero digit is subtracted from 10 and the result is written in the complement, tens complement. Then all other subsequent digits must be subtracted from 9. I will explain with an example. Okay, we will see the computation of tens complement using the shortcut method. So the least significant digit 0 or zeros in the least significant bit positions. So the first non-zero bit is 1. Non-zero digit is 2. So all the zeros up to this first number non-zero digit can be retained as it is. So 0 is copied to the result as 0 itself. Then the first non-zero digit how to be subtracted from 10. So 10 minus 2, the answer is 8. Then all other digit must be subtracted from 9. So 9 minus 5, the answer is 4. 9 minus 2, the answer is 7. 9 minus 5, the answer is 4. So we got the same result as we have computed using the equation method. Then we can see one more example, tens complement of 0.3267 to the base 10. So here are no zeros. So the first non-zero digit is 7. So 7 need to be subtracted from 10. 10 minus 7, 3. Then all other digits are subtracted from 9. 9 minus 6, 3. 9 minus 2, 7. 9 minus 3, 6. So the answer is 0.6733 to the base 10. This is the shortcut method to find the tens complement. Then there is a shortcut method for finding two's complement also. It is just explained here. Leave all least significant zeros and the first non-zero digit unchanged. Then replace ones by 0 and zeros by ones in all other higher significant digits. Okay, we can explain the rules with example. It will be more clear to you. Two's complement of 10110 to the base 2. The answer is, so we have to move in this direction. That is from this direction, from right to left. So the first non-zero digit is 1. Up to this position, we have to write these numbers to the answer without any change. That is 0, then 0, then 1. Okay. Then for this part, that is 101, what we can do? We have to change 1 with the 0, 0 with 1, and 1 with the 0. So the answer is 0, 1, 0, 1, 0, 0 to the base 2. Then we will see another example, two's complement of 0. Here we have to take care. 0.0110 is actually 0.0110 itself. So please don't change this 0 to 1. Then you will get a wrong answer. Assume that this much only, that is 0.0110 to the base 2. So the first non-zero digit or 1 is this one. So up to this one, we have to copy to the final answer, that is 0, 1 as it is. Then we have to replace this 1 with the 0 and this 0 with the 1. So the answer will become 0.1010 to the base 2. Thank you.